We have an op-amp circuit with a constant voltage source that's being switched at t equals 0 with a capacitor in the circuit. We want to find the output voltage V out as a function of time for t greater than 0. Now the first thing we want to do is develop a strategy for how to do this problem. The circuit has one energy storage element. It's a capacitor. That means this is going to be a first order circuit. After the switch closes, the forcing function, or the source, which is providing energy to the capacitor, is a constant. So we essentially have a constant input. So the form of the solution, V out of t, will be some constant k1 e to the minus t over tau plus k2. So now we just have to find k1, k2, and tau. We have a couple of different approaches for finding tau. This is an RC circuit. So if we take advantage of the fact that this is an RC circuit, tau is equal to Req times C. Unfortunately, Req in this case is a little bit tricky. The op-amp itself is acting kind of like a dependent source. Independent sources we get to kill directly. We can short the voltage source. If there's a current source, we convert it to an open circuit. You can't do that with dependent sources, so this becomes a little bit of a problem at the moment. The other approach is to use the differential equation governing the circuit. In standard form, first order differential equation would be dV out by dt plus 1 over tau V out is some forcing function f of t. This approach will always work. So when we're solving this problem, let's use this approach first. After we do that, let's talk about how to find an equivalent resistance and use this approach for a circuit that contains an op-amp or some other kind of dependent source. So let's write the differential equation governing this circuit. We need to write the differential equation for t greater than 0. So for t greater than 0, this switch is in its closed position and the circuit looks like this. So if we're going to write a differential equation for the circuit, we'll need the voltage current characteristics for the energy storage elements. For this capacitor, in that case, I'll define a voltage V sub C that says that the current going into this terminal is 2 farads times the derivative of V sub C with respect to time. Now I've got my passive sign convention taken care of, and I don't have to remember the voltage current relationships for the capacitor anymore. Now let's apply our op-amp rules. If I say that this node here is at 0 volts, that's our reference, then this terminal is at 0 volts. That means that since there's no voltage difference across these two input terminals, this voltage here is 0 volts. Now the next step is probably to do KCL at the input terminals. If I call this node A, KCL at A says that this current through this 20 ohm resistor is 0 volts minus 3 volts over 20 ohms, plus the current through the capacitor is just 2 dVc by dt, plus the current through this resistor is going to be this voltage V sub C divided by 20 ohms. That sums to 0. Now we've got one equation and one unknown, which we can solve for V sub C, but what we really need is V out. So let's write V sub C in terms of V out. V sub C is the difference between 0 volts here and V out, with the 0 volts being the assumed higher voltage terminal. So V sub C is just equal to 0 minus V out. So V sub C is just the negative of V out. I can plug that in here and I can plug it in there. Taking the 3 over 20 to the other side, I get 2 times dV out by dt with the negative sign to keep track of this sign change, minus V out over 20 is equal to 3 over 20. Now writing that in standard form, I divide out this negative 2, so I get dV out by dt plus V out over 40 is equal to negative 3 over 40. So now before I really go any further with this, I'm probably going to want to check to see if this differential equation is correct. For a first order differential equation, it's probably not that hard to solve. But as your systems get to be higher and higher order, you're going to want to make sure this is right before you start solving a 65th order differential equation. So let's check V out as t goes to infinity based on our physical understanding of how this capacitor works versus the final value that's given to us by this differential equation. So as t goes to infinity, our input's constant If everything's constant in the circuit, the capacitor looks like an open circuit, and our circuit will look like this. So we have no current going through here as t goes to infinity. Now, let's do our same analysis. If I still choose this as our 0-volt reference, this is 0 volts, this is 0 volts. So if this is node A, KCL at A says that 0 minus 3 volts over 20 plus 0 minus V out as t goes to infinity over 20 is equal to 0, multiplying through by 20. V out as t goes to infinity is equal to negative 3 volts. Now let's check that against our differential equation. So the differential equation we got previously was dV out by dt plus 1 over 40 V out is equal to minus 3 over 40. Now as t goes to infinity, since this forcing function is a constant, the derivative of the voltage as t goes to infinity with respect to time is 0, because V out has to become a constant. So if this goes to 0, 1 over 40 times V out of infinity is equal to negative 3 over 40. Cancel that with that. So our differential equation says V out of infinity is negative 3 volts, which agrees with our result based on our physical insight on how the capacitor behaves as t goes to infinity for constant inputs. So we have a lot of confidence in our differential equation now. So let's go ahead and proceed with the solution. So if this is our solution, the term multiplying V out with this multiplicative factor being 1 is 1 over tau. So 1 over tau is equal to 1 over 40, and tau is equal to 40 seconds. We've already decided that the form of the solution was going to be V out of t is equal to K1 e to the minus t over tau plus K2. So now we know that tau is equal to 40 seconds. Now let's take a look at the final condition as t goes to infinity. Both the differential equation and the circuit's physical behavior told us that V out at t equals infinity is equal to minus 3 volts. So if I plug infinity in for time up here, I set this equal to K1 e to the minus infinity plus K2. E to the minus infinity is 0. So this tells me that K2 is equal to negative 3 volts. Now finally, let's take a look at the initial condition. So t equals 0 plus. Just before this switch closes at t equals 0 minus, there's no voltage applied to the capacitor. If we assume that that switch has been open for a long time, this capacitor can have no energy stored in it. So V sub c at t equals 0 minus is equal to 0 volts. Capacitors can't change their voltage instantaneously, so this is V sub c at t equals 0 plus. And we already said that V out is equal to minus V sub c up here. So V out at t equals 0 plus is equal to 0 volts. If I plug in 0 for time, that's equal to K1 plus K2. If I plug K2 is equal to negative 3 there, K1 is equal to 3 volts. And now we can write the final solution. So V out of t is equal to 3 volts times 1 minus e to the minus t over tau, which is 40 seconds. That's in volts, and that's for t greater than 0. Now let's go back and try to use the equivalent resistance seen by the capacitor to determine tau. So let's find tau from the capacitance and its equivalent resistance. This is an RC circuit. So tau is equal to Req times C. We just have to figure out what Req is. Now, to find Req, we kill the independent sources. So the voltage source is going to become a short circuit here. Now we have to figure out what the equivalent resistance is seen by the capacitor, essentially the Thevenin resistance. So we take the capacitor out and we look for a voltage-current relationship at these terminals. So Req is equal to the voltage over the current seen by these terminals. Now, I can't kill this guy the way I kill this source because this is essentially a dependent source. The voltage it puts out depends on what's going on elsewhere. So I can't just short anything or open circuit anything. But what I can do is a much more general approach. I can actually put a little voltage source between the terminals where the capacitor was. So apply a voltage there and calculate the current going into the rest of the circuit. So then the equivalent resistance is simply going to be whatever voltage I apply divided by whatever current I solve for. I can also do exactly the opposite. I can put a little current source between these terminals, solve for the resulting voltage, and still apply this relationship. So I'm going to arbitrarily apply a 1 amp current here, solve for the voltage resulting from that, and then use this equation to calculate an equivalent resistance. So I've put a 1 amp current source here. That just makes my life easier because ultimately a 1's going to go in here and Req will be V sub s over 1, and that makes my math easy. So if I do this, essentially what I've got is 1 amp. I've got an equivalent resistance, Req, which includes the effects of this op amp if I solve for this voltage, V sub s. So Req will be V sub s over 1 amp. I solve the circuit exactly the way I would any other circuit. I'll make this my reference terminal at 0 volts. That means this is 0 volts. If this is 0 volts and this is all shorted, then the voltage difference across this resistance is 0 volts and this current is 0 amps. Now if I do KCL at A, I have 1 amp going this direction. I have 0 amps going here because I have 0 amps into the op amp and 0 amps through that 20 ohm resistor. So the entire 1 amp current has to go through this 20 ohm resistor. And directly by Ohm's law, I have 1 amp times 20 ohms is 20 volts. So KCL at A essentially tells me that V sub s is equal to 20 volts. So Req is equal to 20 volts over 1 amp, which is 20 ohms, and tau is equal to Req times C, so that's 20 ohms times 2 farads, which is 40 seconds, which is the same thing that I got before.